want to estimate the cost. We need to do the computation. We need to really calculate the number of time units. After that, we need to think about, can we improve that performance measure? Yeah. All right. So that's the, our plan. Yeah. Continue our analysis this time. Yeah. Yeah. All right. So let's work on our first subproblem. We want to count the number of additions, total number of additions. Yeah. When you look at the formula for this general polynomial expression, can you tell me how many number of additions we need to take? Give me some number, give some expression. I treat as a guess. It's similar to the way we did before. Yeah, because we don't know it's correct or not, right? Yeah. So our first guess, yeah. So treat first guess, n minus 1. Okay. Any other guess, different guess you want to make?
N plus 1.
N plus 1. Any other different guess you want to make? We want to see which one is correct. Nobody guessed n, because we only need to be very close, right? N minus 1, n plus 1, why not n? Why not n? Is that a reasonable guess, n? Possible? All right. After this guess, what should we do next? Verification, right? Can you do verification? Right? Okay, yeah. When n equals 1, our P of x equals a0 plus a1x. How many additions do you have? One.
Wait, 2 or 1?
Addition. To ignore multiplication. Plus sign. Count the number of plus sign. Is it 1? All right. Let's do another one. N equals 2. P of x equals a0 plus a1x plus a2x squared. How many additions? 2. It's enough, right? Can you go back to check your guess? Which one is correct, your guess? And is correct. See? Yeah. Guess and verify. This approach. Okay? Guess and verify approach. Right. But it's not enough. Here, I want to introduce another method to do the counting. Here, actually, we're doing the counting. Yeah. So you learn the counting techniques in your discrete math. Discrete math, you learn many basic counting methods. Here, when we do the counting, look at this formula. Basically, we need to count the number of plus sign in this formula. But the question is, here, there are so many terms, and we use ... to represent large number of intermediate terms, because we cannot write them out. All of them, write them out. We cannot do that. So we use ... But when you use ... how do you keep track of all the terms? If you cannot keep track of all the terms, how do you count all those number of plus signs? You need some reliable method to count all the plus signs without getting lost. Because if we cannot keep track of ... we may get lost. Okay, yeah. So we need some method to help us keep track of all the terms. Okay, yeah, here I introduce you a simple method to do that. Yeah, so what's that method? So I call it counting by reference. Counting by reference. You need to find appropriate reference so that you can keep track of all the terms. Actually, based on your everyday experience, you do a lot of things by certain reference, right? Yeah. Otherwise, so a lot of things, it's not easy to describe many things without reference. Yeah, here we do the similar way. Yeah. Let me describe this method first. The essence of this method, yeah. We want to discover one-to-one correspondence between two mathematical objects here. Two mathematical objects. So here I use abstract terms. Yeah. Later I will do the translation. Yeah. Yeah. So we do like this. Here I use a small diagram to show you the idea. Yeah. We have object 1, object 2, and we find some one-to-one correspondence between object 1 and object 2. Okay, all right. So then, for object 1, it's hard to count. Number of object 1, relatively hard to count, because how to keep track of all the objects. Yeah. But for object 2, it's easier to count. Because we know there is a one-to-one correspondence, then how about we just count the object 2 instead of counting object 1? Then use number of object 2 as the same number for object 1. How about this idea? Yeah, this method is called counting by reference. Yeah. Now, in this here, let me show you how to do the counting here. Okay, yeah, yeah. All right, let me show you. Object 1, yeah. Oh, yeah. Yeah, yeah. Plus sign. So bad. Yeah, plus sign. Okay, yeah, plus sign. All right. And hard to count. Object 2. Can we associate plus sign for another different mathematical object? Here, the first plus sign I associate with the subscript of first A1 coefficient, subscript 1. Okay. The second plus sign I associate A2, the subscript of A2 coefficient, and so on. The last plus sign I associate with the subscript of AN coefficient. Okay, yeah. So now I have object number 2. Yeah, let me say AK. Oh, what's wrong? Yeah, AK. Yeah. All right. Yeah. Okay. Yeah. Yeah. Now you can see for plus sign, it's hard to keep track of. Now we shift to counting the number of subscripts, because there is a one-to-one correspondence. Each plus sign, it can be mapped to one of the subscripts. A0, there is no association. A0, okay? Yeah, the first association occurs at A1 because there is no plus sign in front of A0. Okay, yeah. Now, can you tell me how many plus signs, how many subscripts? A1, A2, A3 through AN, how many subscripts? A1 consecutive integers, 1, 2, 3, no gap, no missing term through N, counting from 1 through N. How many numbers? N, right? Easy, right? Easy to keep track of. Much easier than counting number of plus signs. So we make that switch. So you can tell me the number of additions N. How about this method? Yeah. Okay, counting by reference. All right. Yeah. So we get an answer N additions. Yeah. All right. Yeah. All right. So then, okay. Subproblem number 2, count the number of multiplications. So this time, it's not hard because we already did for the general term, that representative, the general term. Yeah. So let's do the work, calculate the number of multiplications. All right, yeah. So here we already did this part, so I can go a little faster. Yeah. All right, so now let's do the chart. All right. K equals 1 multiplication. K equals to 2 multiplications, and so on. Okay, all right. So the total, let's add up all these numbers, and we know the formula, the summation of these n consecutive integers from 1 through n, thus 1/2 times n plus 1. This formula. We know it. Yeah, this formula. Okay, yeah. All right. Can we get the number of units? Yeah, because we already know the number of additions, number of multiplications. Can we calculate our final number of total time units based on our assumption? Yeah, all right, yeah. Yeah, so here we did this part, yeah, but we need to calculate the total number of time units. Yeah. For the addition part, contribution from addition, n units, right? Yeah. Each one unit, we have n units. But for multiplication, each multiplication, there are 10 units. 10 units. 10 times 1/2 n times n plus 1. Yeah, 1/2 times 10. So that's 5. So you get this expression. 5n times n plus 1. All right. So the total number of time units, 5n squared plus 6n. So we complete that first part, the measure part. Some objective measure. We get objective measure. The second part, we need to improve it. Now we can try to improve this method. Although at this point, we do not know how to improve. We do not know how to improve. But at least we know we want to reduce this number, 5n squared plus 6n. We want to reduce this number. Okay, so the goal of our next round, we try to reduce this number significantly. Yeah. So, all right. So, yeah. How to do it? Yeah. All right. Yeah. Improvement strategy. How to improve it. Yeah. Let's do some observation here. Because at this point, we do not have any idea. We want to do some experiments to find some useful properties. Useful properties. All right, yeah. So what property we want to find? Yeah, here. Yeah. All right. So first, let's look at the cost ratio. The cost ratio. 10-to-1 ratio. The cost of multiplication operation versus addition, 10-to-1 ratio. Yeah. Then, you know, from the total response time, big part of it, there is a very big part of the response time used for multiplications. Yeah. So you know that. Yeah. All right. So our conclusion, in order to reduce the total number of time units, our focus should be on multiplications. Our focus should be on multiplications. Here, the reason, let me explain the reason, you know, using a simple diagram here. Simple diagram here. So, yeah, I mean, all right, yeah. So I draw this big circle represent total number of time units. Yeah. And other than this small portion, the big part, the remaining big part, all for multiplication. Yeah, to right. Yeah, multiplication. Okay. Yeah. So here you can see if you put your resource in the addition part, then the improvement room is very small. Very little you can improve. So we should put our computing resource, our main resource, on the multiplication part. Then there is a large room we can make reduction. That's the reason, because that big part, a lot of room, you can make improvement. Yeah. All right. So, yeah. So now let's apply this strategy. Yeah. Reduce the number of multiplications. The gain is big. Yeah. We know the gain would be big if we work on this important part.